Hi everyone, Eric here with another physics problem for you. This one is going to be an acceleration of a system with friction. It's going to be another one out of the book. I simplified it a little bit because I didn't feel like dealing with this chord here. But this one is number 24, chapter 5 in the book. And it says, determine the formula for the acceleration of the system shown in terms of m1, m2. Define any other variables needed. Kind of an open-ended question, but I'll just solve this the way I normally solve this and what usually the professors at MSOE expect. So here we go. So first I'm going to take a look at my system. It's a pulley with two masses. The masses don't necessarily have to be equal. We're not given the number for the quantity of mass that's here, but it doesn't matter. We're going to just do this whole problem with variables. Since this is chapter 5, there is friction involved here, so we won't ignore that term. And what else? That's about it. The first step I like to do, as always, is draw my forces. So I personally do it for this whole system all at once. And then later I split it up. So we'll just do it my way. Mass 1, there's going to be, again, the force of gravity straight down. Let's undo that. Let's make it a line, an arrow. Force of gravity straight down. And then I always think there's a reason why this block doesn't just fall through this plain box here. And that's because there's a normal force straight up holding it up. There's also going to be a force tension pulling this thing to the right. So let's draw that. And then there's friction involved. So there's force friction to the left. Friction is always going to be opposite of your movement. Just keep that in mind. All right. And then for this block, there's force of gravity down and then force tension up. And since this isn't touching the wall, there's no friction or normal force. We're also told to ignore the friction in the pulley. So we're going to ignore that. We're going to pretend this pulley is just a perfect ideal pulley. Now the next step is we then think about what equations I need to know to solve for the acceleration of this problem. And again, lucky for me, I have my equation sheet. And for my equation sheet, I wrote what I think I would know. I've drawn forces and I need to find acceleration, and there's masses here. So F equals ma is the smart choice here. Newton's second law. It's a good go-to if you're taking physics 1 and you're just problem solving in general. It's always worth trying F equals ma. If the question asks for acceleration. But okay, so now what I should do is, and here's the tricky part of this problem, is that I should define a coordinate system. I'm gonna do two separate ones for a different one for each mass. For reasons maybe you'll see. But for this one, I'm going to draw my coordinate system like this, where this part is my I hat, and this part is my j hat. So going up and down is my j direction, going left to right is my I direction. And then for the second mass, I'm going to draw my coordinates like this. So I can either call this way j hat or I hat. I'm going to call it I hat in this problem. It doesn't really matter what you call it as long as you're consistent um, when you move forward. So I'm going to call it I hat just for now. And you'll see what I mean by consistency, but this is the tricky part. So this way is I, up and down is I, and then this one's going to be J. Okay, for Maths 2. All right, so now I can begin writing force equations for this problem. So let's start for Maths 1, my sum of forces for F, I'm going to just use F equals MA. I'm going to sum up all my forces on Mass 1, and then maybe solve for an acceleration. And then I'm going to do the same for Mass 2. So let's start with Mass 1. So let's look at the sum of forces for 1. It's going to equals M1A. And then I can expand my sum of forces to, and I'm going to plug in an I hat here. This is an I. I was going to draw an X, but I turned it into an I. That's why it's kind of messy. Well, let's just redraw that. So call this I hat. All right, sum of forces of mass 1 in the I hat direction is equal to M1A. And then my forces are going to just be my force of friction, so comma, so negative force of friction because it's to the left, and I've defined to the right as positive, plus, since it's a sum, my force tension from the rope. So force tension equals M1A. All right, cool. Then I'm going to do my sum of forces for F1 in the J direction is equal to M1A. In the J, I should define this as I, this A. Now, something to think about is that I always ask myself, is this thing accelerating in the J direction at all? If this thing moves to the right only, then there's no change in position in the J. So I can say this acceleration goes to 0. So my sum of forces in the J should equal to 0. And then my forces in the J are, this can expand to negative my mass times the force of gravity. It's my force of gravity, but I'll just call it force of gravity for now. Fg plus force normal is equal to 0. This is my Fg, this is my force normal. Now the next step is that this thing, once my question asks for the acceleration of the system in terms of m1 and m2. So I need to figure out how to expand Fg and Fn in terms of mass. But I know the expansion of force of gravity is mass times the variable g, or constant g, sorry. Mass 1 times g plus force of normal, which we don't know, but we know it has to be equal to 0. So this is what I end up with. And now I can solve for force normal. So force normal is going to be equal to m1g. So now I've written my force normal in terms of mass m1. So my next step is I can plug in up here these terms in terms of m1 only. I can start to do that. So let's do that. Let's also call this equation 1 here. So label this 1. And another equation I'm going to need is my force of friction by definition is equal to mu force normal, which is kind of enlightening and explains why I defined force normal in the y direction. So I can write my force of friction now in terms of mass 1. If I make a substitution, mg goes into Fn here. So what I get here is that this is equal to mu times mg m1g plus force tension, this is a negative still, equals m1a. All right, so this is really equation 1. I'm going to box this one because that's the one I want. This guy. Cool. All right, now I can look at my second mass, which only has 2 forces acting on it. These are both in what I've defined as the I direction. So let's keep that in mind. Let's go back to my pen and section this off. So then M1, M2, so my sum of forces of F2 in the I direction is equal to M2 times A. Let's put a little head over this guy. Cool. Let's expand my sum of forces again to mg and force tension. Now here's the trick. We have to be consistent with direction. So this is the reason why I've made my I hat down, and I've also decided that this way is positive. Because if I think about this whole system, when this thing moves to the, when this mass 1 moves to the right, mass 2 will move down because they're connected. So you can think of I making kind of like a loop down. So in this system, to the right is positive and down is positive. So when I write my sum of forces, I want to write mg, my force of gravity, as positive, and then my force tension, which is up on m2, is negative. So now I'm going to say force of gravity minus force tension equals m2a. All right. And then again, it asks for this in terms of m1 and m2, so now I have to expand this. So let's expand it. Force of gravity is going to be m2 times g minus force tension equals m2a. All right. So now I have an equation for this system and an equation for, so I have an equation for system for mass 2 and an equation for mass 1. And something else that I've noticed is that my force tension is not defined as anything, and also my acceleration. So I have 2 unknowns, but I have 2 equations, which means I can create a system of equations, which is a fancy way of saying solve one for one variable, one equation for one variable, and then solve the second equation for the second variable, and make a substitution. So since I've done this mostly from experience, I know that I have to solve this one for my force tension. So if I get if I get a force tension term, I can substitute force tension in here, and I'll have the whole my whole acceleration in terms of mass 1 and mass 2. The tricky part here is getting the signs right. I always screw up the signs, but let's try to get it right on camera because that's how we roll. So I subtract M2 over, and then I multiply by the negative. So I should get negative, or I should get Ft. My force tension is equal to negative M2A plus M2G. Did I do that correct? I think so. We'll find out at the end if this step is right. All right, so now I have a term for force tension. I can plug this into this top term into equation 1. So if we call this one equation 2, I can plug 2 into 1 and be almost done. So let's do that real quick. So highlight this guy. I can plug this into here. And what I should get is, I'll write it down here, mu it's going to be black also. I should get mu m1g plus my equation for force tension, which is actually not plus, minus m2a plus m2g for T force tension in here. So minus m2a plus m2g is equal to m1a. All right, now I have to solve this guy for a. So let's go to page 2. I'm going to rewrite this here. Mu m1g minus m2a plus m2g equals m1a. Solve this for a. Move this over here first. So I get mu m1g plus m2g equals m1a plus m2a. All right, now I can factor out an a here, so I get m1 plus m2. Keep clicking the button. A equals mu m1g plus m2g. Divide both sides by this, so I get, divide both sides by this quantity, so I get mu m1g plus m2g over m1 plus m2 equals a. All right, so now I have an equation for this system in terms of m1 and m2. And it's an equation for acceleration, so I'm all done. All right, so let's think about how we can make this problem more difficult, or like something that's test worthy. So something they could do is they could put this mass on a wedge. So it looks something like this. I'm going to draw it poorly, but you have like a wedge here, and then it's connected to a pulley like that. So that can change the problem. And I think this makes it kind of pretty difficult. So try to do something like this when you do the problem. Or they could face the wedge the other way, like this, right? The wedge is faced this way, and there's still a pulley. So that's something that can change. So keep that in mind when you do this problem. The trick here is just knowing you have to substitute for force tension and keeping the signs consistent. If you do that, you should get the right answer. Another way to check if my answer is right is if down here I have M1 plus M2, I can plug in numbers that are all positive and it works. But if I had M1 minus M2, if I try to make both of these masses the same, so let's say like somehow I got my sign wrong and I had a minus. Let's say both masses are 2 kilograms. 2 minus 2 is going to be 0, and it will allow me to divide by 0, which we know isn't actually allowed. So that means something is wrong in my equation, which would probably be these signs here. So just keep that in mind when you do it. If you get a negative sign here, you've made a sign error. Besides that, I think we're all done. I think that covers it. So hope you guys are doing well. See you next time.